This lecture will conclude the kinematics of a simple periodic wave. This lecture is specific to Physics AB and Honors Physics AB. In my previous two lectures describing the kinematics of a simple periodic wave, we always started the clock, that is at times t is equal to 0, when the spring just simply traces out a cosine curve. And then we watched, for example, how that cosine curve propagated with time. However, that doesn't necessarily always have to be how we start off a situation. In other words, the spring itself could look like anything in terms of where it is on the cosine curve at times t is equal to 0. So then therefore, how do you mathematically take this into account? Well, all that we simply do is we introduce into the argument of the cosine function an additional phase shift. This then takes care, mathematically that is, of starting the clock at an arbitrary moment in time. In other words, the kinematics equation for a simple periodic wave is as follows. So that is this expression here. So the additional phase angle phi simply takes care of the fact mathematically that we can start the clock at any arbitrary moment in time. And then the way that this function works mathematically is that as time goes on, these two numbers then add together to give you an overall phase shift, which you then graph with the cosine curve. The easiest way to illustrate this is to once again just do an example, but I'm not going to do as detailed an example as I did in the second part of this lecture. Instead, we'll just take a look at a portion of the graphing procedure, and that's good enough for our purposes here. Okay, so let's go ahead and access the following problem. We're given the following wave. It's essentially the exact same wave as we've seen before in the previous example, but now we're going to have an additional term. So here's the function that we have. That is this expression here in terms of meters. So now once again we have an amplitude here of 4 meters. The wave number k is pi over 4 radians per meter. So then therefore the wavelength is once again 8 meters, just like it was in the previous problem. Right here is the angular frequency omega of pi over 2 radians per second. This then means that the period, capital T, is going to be 4 seconds once again. So all of those numbers are still the same as they were before. As we'll see, once again, the negative sign here will mean that the cosine curve ultimately propagates to the right-hand side. But now we have this additional phase shift to deal with. Okay, here's now what we have in the problem. It's a short version, in other words, of the more detailed example that I did in the previous lecture. It just simply says, graph the propagation of this wave for just 2 moments in time. T is equal to 0 and at 1/4 of the period. So now let's see what happens. First of all, when we set the time t equal to 0. So when we set the time t equal to 0, we now go into the function and set the time t equal to 0 here, and then therefore this term drops out. But we still have the plus pi over 2 remaining here in terms of the function that we now obtain. So, and now here's what I have to graph. First of all, I start off with a cosine curve that's shifted to the left by pi over 2 radians. It looks like I'm contradicting myself here. I said a few minutes ago that the negative sign will mean that the wave will propagate to the right, and that's correct. However, the way that we start out with, in other words, what the spring looks like at this moment in time, is a cosine curve shifted to the left by pi over 2 radians. So here's a little shortcut, first of all, to get the graphing process started. So here's my little cosine curve, and now what I have to do is I have to begin by shifting it to the left pi over 2 radians. Pi over 2 radians is 1/4 of a wavelength. That's this point right here. So now I have to take that point and shift it until it's on the left-hand side of the axis. When I do, that's then how I begin this graph. All right, so let's go ahead and do that. We have x here in terms of meters and y in terms of meters. And now when I start my graph, I start with this point right here. So I'm going to line out here, once again in green, a single wavelength. So this right here is 8 meters. Here's 4 and -4 respectively. And if you look at this graph, it's just a negative sine curve. What we're going to do is we're going to follow this negative sine curve to the right as time goes on now for the next moment in time. Okay, now for the next moment in time, we have 1/4 of the period. So this is 1/4 of 4 seconds, which is 1 second. So now we go into the function and we set the time t equal to 1. Okay, when I set the time t equal to 1, notice that I now have a minus pi over 2 plus pi over 2, which drops out. and then therefore I just simply have the following. A cosine curve. So let's just go ahead and graph that. That is like so. We start off by just graphing a single wavelength. So this distance right here is 8 meters. And here's the amplitude of 4 and minus 4 respectively. And now this negative sine curve that I started with in green has now propagated. It has propagated to this point here. Like so. Notice it is still propagating to the right-hand side of this problem, just like it was in the last problem. It's just that we started the clock when the spring looked like this. That is, at that moment in time. Okay, then the same pattern is picked up as we've already seen. So for example, if we start off with a single oscillator here, it is now oscillated to the here. It has undergone 1/4 of an oscillation in 1/4 of the period. The wave itself is propagated to the right-hand side 1/4 of a wavelength in 1/4 of the period, and so on and so on and so on. So when it comes to doing the homework problems for the kinematics of a simple periodic wave, I want you to do the homework problems exactly as you're seeing me do these examples here. That is, starting off with a curve at times t is equal to 0, giving it a certain color, and then as time goes on, I'm outlining in that exact same color the original wave that I started with, thereby showing its propagation. Okay, that concludes the kinematics of a simple periodic wave.